Hello, I'm Cynthia Rosenzweig, and with my colleague Alex Ruane, we're going to share a Hyperwall presentation on using NASA tools for climate change and food. In the coming decades, the whole world is asking the agricultural sector to take on a triple challenge. What are those three parts of the challenge? It's a three-part challenge. First, sustainably increase production to provide healthy food for all. The world's population is growing up to 9 billion, and we have to do that sustainably, avoiding things like erosion. Second, we need to adapt all the agricultural sector and food production to climate change and to ongoing and increasing, in some agricultural locations, climate extremes. We're showing Hurricane Ian in Florida. Oh, you did, yes. And it affected over 300,000 acres of citrus production when the Hurricane Ian came through. No orange picking. Thanks very much for that a live update. And then finally, at the same time, agriculture needs to mitigate greenhouse gas emissions from agricultural lands because the entire food system is responsible for 30% of human-caused greenhouse gas emissions. And the bottom panel is rice production in India, with rice as very high methane emitter. So, NASA scientists are leading global efforts to apply missions and models to aid agricultural decisions. And I want to introduce AgVIP, the organization that is led out of NASA GIS in New York. And AgVIP stands for the Agricultural Model Intercomparison and Improvement Project. And I'm going to be explaining a lot about how in AgVIP we use NASA tools for agricultural decisions. But what this is showing, this is beginning to hone in on how we use NASA tools. So from satellites, we can get precipitation data, vegetation and the health of vegetation, particularly the agricultural crops, and soil moisture, absolutely critical for crop production. And then we use crop models to integrate all the incoming NASA data, and so that we can really understand the processes of what's going on with the crop production and climate in particular. So zooming out or zooming in to this, so we see satellites at the top, we see our crop growth, we see our management with the tractors, irrigation setups, we see that there's greenhouse gas emissions from agricultural lands, and we also see the farmers, right? There are people involved. Agriculture does not happen without farmers and people. So you can see that it's a very complex system that the tools here for agriculture, we're highlighting in this talk today remote sensing with the weather and vegetation and soil status, and then the role of the crop models, which capture the responses to what we call genotype, but it's like the varieties of crops that are grown, all the environment that the crops are grown in, and then this management piece of how the farmers are what crops they're growing, how they're growing them, what kind of irrigation, what kind of fertilizer they're putting on, and how much and when. So we do all that, but with the NASA models and global climate models, we do this both for the current, the remote sensing really helps up for the current situation, and the global climate models help for the future of climate that we're going to be growing all the crops under changing climate conditions. So this is in Ghana, an AgMIP project that we worked with there. And Garrett, I think you worked with the Ghana. Garrett's here. Garrett Hugenboom is here from University of Florida, and who worked with the AgMIP team in Ghana. And this is the Enhanced Vegetation Index for Ghana from 2000 to 2022. This index tells us what we can expect for wet and dry years. Of course, the yellows are the drought years, and the greens are everything is okay for the crops. What we see from working with the satellite data, what we really can study and understand is that each year is different, but we are able to understand the variability year to year, and each region is different. So how does this help with agricultural decisions? It helps policymakers pinpoint where, when, and how they can help farmers. So they wouldn't want to perhaps help farmers on wet years all across the country. They can, with the help of the NASA tools, and I think it's coming up towards the end of this, 2001 was a big drought year with a lot of yellows, and I think we're coming up here to also some more drought years here more recently in Ghana. Yep. So that's use of remote sensing. And here's what we do with the models. We can identify and prioritize agricultural strategies. So we can say, okay, what happens with the crop that we're growing in the computer if we put on more fertilizer, if we change our irrigation regime? So we can test alternative strategies without having to test every single one out in the field, which is very time consuming. It takes and is expensive. We can also link to this larger food system that agricultural production is embedded in. So we have production, but we also have, with AgMIP, we have teams of global and regional economists who are with us. And we also work with health and nutrition scientists as well. The goal, of course, is to sustainably manage land and water resources. So with these NASA tools, we can scale up. If something's working well, we can then test it in other locations. And on the climate change side, we can help build resilience to the increasing climate extremes and help to reduce greenhouse gas emissions. So this is work in Pakistan. Garrett, you also worked in Pakistan. He was the AgMIP resource person for our Pakistan team. And this is work of the regional economics team. You can see climate change impact on net farm income without adaptation, and then with the adaptation packages that we're helping the farmers to do better under changing climate change conditions. We get vulnerability, estimates of how many of the farmers in a given farming region will be negatively affected by climate change, and then testing the adaptation packages, how they actually then can benefit the farmers right there on the ground. So, stepping back, from all of this, you can see that agricultural information connects across disciplines, right? We have our space data analysts, we have our crop modelers, and we have our economists. It connects across the disciplines, but also across scales. And so NASA, of course, is very much the tools really help from the global scale. Here's the global scale, and then, but also honing down to the regional scale as well. Here's the biophysical, on this side we have, on this row we have biophysical models, regional, local level, and global level. And we have here's the economics, here's the regional markets and prices, and with the global team that's working on the global markets. But through AgMIP, we can connect these scales and disciplines together to really learn about how climate change will be affecting the food system, but also how we can help develop strategies to withstand it. So let's go right to Iowa. This animation is crop model results. Yellow is corn, green is soy, and brightness is how well the crops are doing. So when you get to a drought year, which is coming up in 2012, anybody here from Iowa? Yes, okay, you may remember 2012 with the drought, so that the screen got very dark. because it was not, that was a really negative drought year for the crops. So we're honing in. And the differences that you see are based on, because we use the models to have different varieties, the different environment in the field, and the different management. So this is the kind of thing that we can do. Question, yes?
What's the spatial resolution, the limit of spatial resolution there?
It's down to, I think, 4 kilometers. Yeah. It's very fine resolution. Yeah, I showed this in Iowa recently. They were very interested. They really liked it. I showed it at Iowa State. Okay, so that's showing what we can do now with the crop models. Let's go to the next one. Let's now turn to climate change. These are the annual mean temperature changes projected by global climate models. This is temperatures relative to 1850 and 1900. And these 3 maps are showing simulated changes. This one, if the world is able to hold the global surface warming, temperature warming, to 1.5 degrees C. This is the target from the Paris Agreement. We're focused, of course, on the land regions, the temperature projections there, which of course vary. This is the mean change, but it varies by region. Even at 1.5, we're having changes in our agricultural region. This one is the simulated change at 2 degrees C, which in the Paris Agreement it says we hope at least 2.0, but really we want 1.5, so it's this range is the global goal. Unfortunately, the world is much more headed on this trajectory to 4 degrees C mean global surface temperature warming. And you can see that this, for the agricultural regions, these will be very, very challenging. Now, in between here, 2 and 4, is the 3 degree. We don't have one. I want to get a map of 3 degree. So, Jack, maybe you can help make that happen. Because 3 degrees is what the world has pledged with the nationally determined contributions. But even you can see, think, in between here, even 3 degrees is really going to be significant changes for our agricultural regions. So this is, I wanted to show this, which is from NASA GIST, my very own institute, our very own institute. What we do is, these are back to, I just showed you projections. These are observations of temperature change over land, because that's what the farmers are seeing, from 1880 to present. It's updated every year. What we can see is, really about 1970, the global warming, the observed global warming has taken off. So the urgency of the responding to climate change is growing and accelerating. That's what this increasing curve is really showing. So what we do is we take the global, what AgMIP does, the Global Gridded Crop Modeling Initiative, GGCMI it's called. It takes global climate models, in this case from 5 different GCMs. We always do multi-model approach. This is with 12 different crop models across the world. And then we take the projections of climate change globally and use them to project what will happen to wheat, what will happen to maize. We also do this for soybean and rice. And we look to see through the year. Now let's see, through the year, through the century. Let me see if I can get it back. Good. Okay. So what we see is, again, crops are different, regions are different. Look, if you see wheat, it's a cool season crop. It's the photosynthetic pathway C3 can soak up the CO2 and do a better job with it. And so mainly those are green colors, which means that wheat is doing okay. On the other hand, maize, C4 crop, is much, much more vulnerable to the projected climate change. And look, all through the world, actually, especially though in developing countries, the projections on maize, or what we call corn, is very real. Now, coming back to the U.S., what will farmers be seeing? So, and in terms of climate risks. So let's look first at these little blue changes here. That is no more frost by 2050, that's the projections, or no by, and the darker blue is no more frost by 2100. So look, in Florida, hey, no more frost. So, you know, not all climate change is bad. But look at the northern part of the country. Heat stress coming, new heat threat by 2050, that's the lighter orange, and then darker orange, new heat threat by 2100. So we see that we can really get a handle on what farmers are going to have to be dealing with in the future. Okay, so this illustrates this food system approach, because we no longer just think about agriculture, we think about it in the context of food production and delivery. So we have all the different parts, including trade. So our global economists have trade in their models. That's this import-export part, imports and exports, food aid, very important humanitarian needs. Will be changing, and ramifications of shocks if there's what we saw in the Ukraine war. That shock with the closing of the ports during the Ukraine war has affected food security in Africa tremendously. So this is why we have to take this food system approach, not just really focus just on the production. So now, remember those little icons of the farmers? Because farming is about people. It's always done by people. This is showing the increasingly dangerous climate for agricultural laborers using the NOAA heat index, which is more than 103 degrees Fahrenheit. It has been shown that for workers outside, it's very dangerous. So again, here we have, this is linking back to those three panels, red panels of the climate projections. Let me get back to it. Let's see if I can get back to it. Good. Okay, so this is the moderate emission scenarios. So this is in the middle. This is in the high emission scenarios if the world does not really get its act together to reduce greenhouse gas emissions. So all across the world, agricultural laborers will be affected by the changing climate. These are the conditions in the US here's from the cooler parts of the country, Idaho, Nebraska, California, Texas, and Florida. It's going to get very, very hot. So I think this might be the last tool I'm going to show. So we're very much getting into machine learning now. And we use weather data, just reams and reams and reams of weather data, remote sensing data, and crop modeling data. And what we use them for is to see where we need to improve our crop models. So here we have AgMIP tools, weather remote sensing crop models. Here we have the machine learning, artificial intelligence programming techniques. And here are the outcomes. We compare the estimated crop yields to the observed crop yields, and we can really see which area in the crop model is doing well and which ones we need to work on more. So the example is that in the United States, AI has indicated the important role of frost. We were looking at frost earlier, but so we have to do a better job on that, and floods. I'm looking at Garrett, who's a major crop modeler for AgMIP, and see if he agrees that these, delving into improving the processes, right, is still what we very much need to do. And these AI and machine learning tools are really, really helpful for this. Okay, here are the take-home points. First, NASA applies missions and models to address current and future food system challenges. Agricultural planning benefits from NASA's ability to observe and simulate over local, regional, and global scales and their interconnections. Finally, the agricultural models enable this testing of strategies, right? so that we can actually see what new strategies we need to implement to really develop resilience in our system, in our agricultural and food systems as we go forward. So with that, I want to show you the AgMIP website. Everything that AgMIP does is protocol-based. It's very rigorous, scientifically based. Up-to-date events. We're having a wonderful AgMIP 9 workshop in New York the last week in June, so check that out. All that's news. And to join AgMIP, it's an open network for all. Visit www.agmip.org. And with that, thank you to NASA.